All right, this is section 5.4, really the total change theorem, also the difference kind of between a definite integral and an indefinite integral. All right. First of all, when you have an integral that doesn't have limits of integration, we call that an indefinite integral because it's not, you don't know for sure what you've got. So it's the integral of f of x. All you have to do is find the antiderivative. And so if your function says f of x, then the antiderivative would be capital F of x, typically is what we use. And then you have to say plus c. And it is indefinite because you don't know what the c is, and so you end up getting, a number of functions, c being a bunch of different things. So family of functions, we call it. Now, if you actually have an integral that has limits, so from a to b, then it's a little different. We're going to be able to evaluate it. We're going to actually get a number as an answer, and that number actually represents the net area under the curve, however much is above and below, and whatever the overall net amount is, that's what the integral equals. Okay? I just made a note again that you want to make sure and memorize that list of antiderivatives on page 402. That'll help a lot when you start evaluating these. All right. First, kind of the basic one that we might have done, we did a little bit in class. So indefinite integral. So you could fast forward this if you already know it. So x cubed divided by 3 minus 4. We're going to add a power to that. So x squared over 2. And then whenever you have a constant, the antiderivative is just, putting an x, multiplying it by x, and then plus c. So that's an okay answer, or you can simplify it a little bit. 5/3 x cubed minus 2x squared plus 3x plus c. If you ever want to check your antiderivative and say, gee, I don't know if I did that thing correctly, you can check it. All you have to do is find the derivative. So the check is to do d dx, of all of those. And so no need to do this, but you have 5/3. You'd bring the 3 out in front. Reduce it by a power. Then remember the constant you carry. The 2 you'd bring out in front. The x you'd reduce by a power. And then this, whenever you have 3x, the derivative would be 3. The constant would be 0, so you wouldn't have that. So it looks like here the 3's would cancel out. So you'd have 5x squared minus 4x and then plus 3. See if that would be the same. Yeah, so that works. All right, I wanted to add a ugly mama here. So this is example 2, kind of an ugly mama. Let's say, I think this is number 23. Maybe you have something similar in the book, so you could use this as an example. And I thought it had a lot of different things about properties and exponents and all these different things I could review. So first of all, this would be kind of a complicated integral to do unless you do a little algebra first. So let's kind of take the time to rewrite this. So you know that square root of x is really the same thing as, x to the 1/2. So I'll go ahead and show that work. So x squared plus 1, let's make it x to the 1/2. And then again, this is the same thing as really being able to rewrite each of these over the x to the 1/2. So I'm really writing a lot here as far as showing work. dx is on the top. I've got, this would be, let me go ahead and say what this would be. It would be x squared over x to the 1/2, splitting this up, and plus 1 over x to the 1/2, and then you got your dx still. Now, using your properties, when you divide, you keep the base and you add your exponents. So we keep the x, and then we subtract these exponents. So that's, 2 is the same thing as 4/2, so 4/2 minus 1/2. So we should have x to the 3/2. Okay? And then we've got our plus, and then just bringing the x to the 1/2 up to the top, that would make it x to the negative 1/2. And then all of this is, still has your operator dx. All right. Next step is we're ready to find the antiderivative. So the antiderivative of this would be x, and we would have to add 1. So when you add 1 to 3/2, you're adding 2/2. So that makes it x to the 5/2 divided by 5/2, and then plus. And then if you add 1 to that, you're adding 2/2, which makes it x to the 1/2 divided by 1/2. And then we're having to evaluate it from 1 to 2. You can get quicker at it when you do that, you can immediately go to the 2/5 if you want. So that's going to be my next step. So I'm going to say 2/5 x to the 5/2, and then plus. When you divide by half, that's the same thing as multiplying by 2, right? So we got 2 and then x to the 1/2, and then we're still needing to evaluate this from 1 to 2. All right, I think I'm ready to start throwing some numbers in here maybe. So let's do it. So we got, let's see. So we got 2/5, and I'm going to go ahead and throw a 2 in here. And that's raised to the 5/2 plus 2, and that's 2 raised to the 1/2. So I plugged in the 2 for everything, and then minus, and then now I'm ready to plug the 1 in for everything. So I've got 2/5, and it's 1 to the 5/2. I mean, that's not going to do anything, but I'll put it in anyways. And I got 2, and then I got 1 raised to the 1/2. All right, so that's what I've got so far. All right, so let's start evaluating here. So what in the world is 2 to the 5/2? So off to the side, you could say this 2 to the 5/2 is actually the square root of 2. I'm doing this right here. So this is actually the square root of 2, and then raised to the 5th power. So I'm not sure exactly how you want to handle that. So let's think here for a second. This would actually equal, you'd have a bunch of radical 2's. There's so many ways to do this. But you could have a bunch of radical 2's, and whenever you have 2 of them, you're going to be able to say that that actually equals 2. So you've got 2 of those, so that would be 2 times 2, and then you'd have 1 left over. So that means that 2 raised to the 5/2 is actually equal to 4 radical 2. So I'm going to write that. I've got 2/5. I'm going to have this actually equal to 4 radical 2, and then plus. Now this 2 raised to the 1/2 is actually just the square root of 2. So I got 2 square root of 2 now. Again, that's just square root of 2. And then minus. And it's minus that whole quantity. So I'm just going to go ahead and keep those parentheses. So that's 2/5. And then plus, and then, that doesn't do anything, so that's just a 2. All right, so it's ugly, but let's see if we can do any combining at all. Do a little bit. All right, so far I've got, I could do the 2 times the 4 here, so I could say that's 8, radical 2 over 5, and then plus. If I really wanted to, I could put a little denominator on this. I could change it, but maybe I'll do that in a second. So I'll say plus 2 radical 2, and then I'm going to go ahead and I'm going to combine these two, the 2/5 and the 2. So common denominator, the 2 would be 10/5. This is 10/5. So let's just say we combine those, so that would be minus 12/5. Would you agree? So it would be minus 12/5. All right, so that wouldn't be a horrible answer. You, of course, could try to get common denominators and work it out from there. For example, like maybe you could put a little, multiply this top and bottom by 5. And if you did that, that would make this right here a 10. So it'd be 10 over 5. So I'll just give you one more simplified answer here. If I was, again, to make this part, if I make this equal to 10 over 5, the 2, I could change that to 10 over 5 to get a common denominator. Then I could add it with the 8. So final answer on this one would be 18 radical 2, and then fortunately the 12/5, that already has a 5 on the bottom. So 18 radical 2 minus 12, all of that divided by 5. So that's just using all of your algebra skills to try to combine the like terms, the like radicals, if you will, getting common denominators, yada, yada. So I wanted to give you an ugly one. All right. Total change theorem. So total change theorem says that whenever you have an integral of a derivative, so the integral of a rate of change, that's what this is because it has the f prime, equals the total change. So integral of the rate of change is the total change from A to B, whatever your limits of integration are. So that's a big theorem. It's really just the fundamental theorem of calculus. It's just that, this because the capital F, is the antiderivative of f prime. So just an application of the fundamental theorem of calculus. Now, of course, you remember the oil spill when we had the different rates that the oil was leaking out. I think by hour 8, over here at hour 8, we were up to like 720 gallons per hour or something like that. And if we wanted to, we could have plotted the rates. And really what we were doing there is we were figuring out all that area under the curve. And it was cool because all that area under the curve was how much oil actually spilled out. So that was an application of this, what we're talking about today. The integral of the rate of change is the total change. This was the total amount of oil. All right. Let's say we have another example, and we say that P of t is the population for any number of years for a particular city, nation, world, whatever. P prime of t is the rate of change of the population. So how is the population changing with time? So if somebody gives us the integral from 5 to 10 of the rate of change, we know if we were to interpret this or write it another way, we certainly could find the antiderivative, and then we could just plug in the limits of integration. And so this is what it would be equivalent to. And what that would represent is that would be the total change in the population. Total change in, I'll just say pop, from 5 to 10 years. If it was years, if the problem was in years. Okay? Certainly, if you had the function, if someone gave you the population function, then you wouldn't really need to do this integral business. All you would do is, plug in a 10 into the p function, and then you would plug a 5 into the p function, and then you'd just be able to subtract those values, and you'd easily be able to figure out, the change in the population from 5 to 10 years. A lot of times, though, we don't have the original function. We just have rates. We have data that gives us rates of change of the population. So if that's the case, then the calculus comes in handy. Righty. I don't know why I put an A. I didn't really do a B there. Okay. Most common application to this, that we'll see, especially on the AP test, is motion. Okay. Derivatives, antiderivatives, integrals. It's really about motion. So let's say we have a function that's the velocity, function here, velocity curve, and we have these different times, t1, and they give us how much area, is in each of these spots here. So this is area 1, area 2, and these are given as positive numbers. Okay, they're just given to us as positive amounts. So if we wanted to find the displacement of this particular object that's moving in a straight line, then the displacement would be the change in the position from time 1 to time 4. So let's say, hey, I want to figure out how this thing has changed its position from time 1 to time 4. All you'd have to do is the integral, because that's what the integral is. It's the change in the position. It's the overall net area under the curve. And so that would be the integral. And the way that we'd calculate that is we would say, okay, we'd have to have the A1, and then the order of this, we could add the A3 because it's above the x-axis. And then we'd have to subtract out the A sub 2 so that we could get the proper amount of net area under the curve. Okay. Now, if we wanted total distance, then we don't care whether it's going forwards or backwards. We've got to accumulate all of that, distance that we've traveled. So then it would be a little bit different, and so then it would be v of t, but what we could always do with the velocity function is we could just put absolute value bars, and that way, even if it was going down like that, it actually would pop up over the x-axis, and then it would be able to accumulate all of that distance so that we wouldn't lose out the stuff underneath. Okay? So as far as the way this setup is, you would just add them all up then. A1 plus A sub 2, and then you wouldn't lose any of your areas, and you get the proper amount of distance traveled. Let's look at one example that we kind of looked at a little bit in class. The velocity function is given, and I really like using the calculator on this. If you're given the function, you could graph it to get a feel for what's going on there. And so at 1 second, it's way down here at -6, and then at 4 seconds, it's up here at 6. So you can tell that from 1 second to 3 seconds, seconds, it's moving backwards or left, whatever you want to say, and so it's moving in the negative direction because it has negative velocity. Then at 3 seconds, it's moving forwards again. Now the displacement is the easiest thing to do because then you would all you have to do is find the integral from 1 to 4 of that particular function, and that would be nothing more than just plugging that into your calculator and figuring out what that integral equals. So we definitely want to just do that real quick, make sure we're all comfortable with that. So here's my calculator, and it looks like that, of course. And then you just I put it into y1 equals, so just put the function in there, and then get out of there, and then we just do math 8 and vars, y vars, put the function in there. Now this is the old school, remember? And then I got x, and then 1, and then comma 4, and I got negative. Just kidding. What the heck? Sorry, I lost my brain for a second. I'm just testing you guys. So math 9, you can see I did it right above, so good enough. y1, x, comma 1, comma 4, negative 4.5. Okay? So you're okay with that. So math 8 derivative, math 9 antiderivative, or integral. All right. Back to the scrapbook here. Okay. Now what does that mean exactly? If the displacement is negative 4.5, then what in the world does that mean? That means that between the time period of 1 and 4 seconds, the object has moved negative 4.5 meters, if it's meters. Let's say this was given in meters, perhaps. Then that means that the position is negative 4.5 meters from where it was at 1 second. Okay? Total change in position. So definitely want to write something like that. So we'll say, so it is 4.5 meters to the left of where it was at 1 second, you know. Makes some sense? Okay. Now the distance is a little bit different. We really need to accumulate, you know, all of this area, and we need to accumulate all that area as well. So what we're going to do is we're going to say we're just going to do the same thing, 1 to 4, but we'll just make sure that we've got our velocity function in absolute value bars so that we get a total distance. So back to the calculator for a second, just make sure we're good. You can do this a couple different ways. You could go back and change your function and kind of insert your absolute value bars. So you could just say abs. I know you guys have the new operating system, so it's a little nicer looking. But just make sure it's absolute value of that function. So then when we go to graph it, it pops that part up, so that's kind of cool. And then we get out of there, and we go math 9, and then we don't want to do that. So we go math 9, and it's a little bit harder on this darn computer. So y1, comma x, comma 1, comma 4, and there we go. So we should get, tell me when we're going to get 10 something. It's thinking slow. Okay, so I got 10, yeah, I got 10.167. So we're going to say that would be 10.16, let's say 7. It's approximate whenever we abbreviate or round it off a little bit. Meters. And that means obviously that's the total distance traveled from 1 to 4. So good. You can do this analytically without a calculator. It's kind of a little bit of a pain in the butt, to be honest. But what you would do is you take your velocity, and you'd have to kind of know where the velocity, where it had changed directions. So you'd go ahead and factor it and find out those critical numbers. The negative 2 doesn't make any sense for time. So, and plus we're just looking at from 1 to 4, so that wouldn't be really affecting us. We do a little sign chart, and we find out pretty quickly that when you're to the left of 3 seconds, we can tell the result is negative, so we knew it was going, to the left. And then we could tell from the sign chart that when we're to the right of 3 that it's going positive. So you actually need to split up your integral. So if you're going from 1 to 4 and you want to find total distance, then, well, let me back up. If you're doing displacement, then you could just do 1 to 4 and you're fine. You just would do the antiderivative of this function, and whatever you get for your integral, that's the displacement, so that would work. But total distance is the one that's a little tricky without a calculator. So you split up your integrals from 1 to 3, and if you do 1 to 3, you just have to make sure again that you put absolute value bars on your function, or when you know that it's going to be negative that whole time, then what you do is actually switch all these signs. So it actually would be from 1 to 3, you would change all these signs if you wanted to find the antiderivative and actually have it be accurate. You would change all the signs, and that way you would get an answer that would be positive, okay? And then this one over here, you already know if you did the antiderivative of this, you get a positive answer. And so for the one on the left, you should get, 7 point, if you do the antiderivative correctly, then you would get 7.333, and then over here you would get 2.8333, and if you, well, I don't need that one. So if you added those together, you would get your 10.167. So you'd have to break it up like that, okay? But I think it's a lot easier with the calculator, obviously. All right, I think that should do it for us.